Hello, everyone. So it's not a presentation if it doesn't have a technical glitch, right? So sorry for starting a little bit late. We have hopefully got this working. So today I'm going to talk about the support for PyTorch at Google from cloud to edge and all the different efforts that we have to make sure that PyTorch works with our ecosystem and for our users and customers really well. My name is Shauheen. I lead the ML frameworks and ecosystem at the cloud accelerators at Google. And today I'm going to talk about PyTorch on cloud TPUs using OpenXLA. Cloud TPUs are designed to scale cost efficiently for a wide range of AI workloads, from training and fine-tuning to inference. And cloud TPUs provide the versatility to accelerate workloads on leading AI frameworks, including PyTorch and JAX and TensorFlow. One of the most important features of TPU systems is the hardware-software co-design that enables a robust and performant solution to train ML models across tens of thousands of chips, scaling in a fault-tolerant and reliable way that is key to many large ML workflows. At the core of the software layer is the OpenXLA compiler. Whether your workflow is in JAX or PyTorch, you can utilize the XLA compiler to achieve high performance by overlapping compute and communications when needed, and to optimize the workload execution when the compiler finds an opportunity for improvements. PyTorch XLA is a library that enables efficient use of PyTorch on XLA devices, such as cloud TPUs. As a fully open source project, PyTorch XLA wants to support and grow the community of developers by providing tested code examples, best practices for performance optimization, and engaging directly with the users and developers. Providing interoperability between GPU and TPU should enable Google Cloud customers to achieve top performance regardless of the hardware they choose, thanks to the capabilities of the OpenXLA compiler. Finally, a strong ecosystem of third-party products and libraries such as Hugging Face and PyTorch Lightning enables easier use of PyTorch on cloud TPUs. PyTorch XLA provides a backend for Torch Dynamo. The flexible architecture of PyTorch 2 allows various backends, such as Inductor and XLA, to provide compilation capabilities for PyTorch workloads. This means that with minimal code change, you can utilize different backends which may have different characteristics in how they compile and execute your model. By utilizing the OpenXLA backend, PyTorch ops are converted to stable HLO ops. And once the model is in stable HLO, you get all the benefits of using the XLA compiler, the distribution mechanisms, the op fusions, and better performance that comes with the XLA ecosystem. Finally, PJRT and Pallas, which are the same runtime and custom kernel language from JAX, can be used for running your PyTorch models on cloud TPUs. So let's talk about performance a little bit. Training large language models would benefit from high model flops utilization. So MFU is the ratio of the observed performance to the theoretical maximum performance of the benchmark hardware setup. We're operating at peak flops with no memory communication overhead. The higher utilization means that you are able to better take advantage of the hardware. In this case, training Llama 2 at different parameter sizes of 7 billion and 70 billion parameters on cloud TPU v5p can achieve up to 55 and 56% MFU respectively. Furthermore, with the integration of JAX and the use of custom kernels such as megablocks, you can ensure best performance for other types of models such as mixture of experts. Now, once your model is trained and for inference, you can use Jetstream for PyTorch, which is an efficient inference solution on cloud TPUs that can get you up to 8,471 tokens per second, serving a Llama 3 with 8 billion parameters on TPU v5 E8. So what is the developer experience like? This is a sample code for fine-tuning Gemma using PyTorch on GPUs. You can define your tokenizer, your LoRa config, load the dataset, and use the supervised fine-tuning trainer and a dataset that you choose. And here are the changes that you have to make to use PyTorch XLA. You add an import statement for PyTorch XLA. You need to replace the CUDA device with an XLA device. And finally, you need to add the XLA FSTP config, which basically tells PyTorch XLA how to run FSTP v2 with gradient checkpointing using the XLA backend. And the rest stays the same. You define the tokenizer, LoRa config, load the dataset, and run your supervised fine-tuning on your Gemma model. And this code runs on cloud TPUs. On a TPU v5p8, you can achieve 71% MFU for the 2 billion parameter model and 64% MFU for the 7 billion parameter model. OpenXLA enables scaling distributed workloads efficiently through the automatic parallelization API. The XLA compiler transforms a single device program into a partitioned one with proper collectives based on the user-provided sharding hints. PyTorch XLA enables developers to write PyTorch programs as if they're writing one single large device program. Now, sometimes finding the best optimized set of parameters for the sharding may be difficult, which is why we have introduced auto-sharding policy. And my colleague actually presented this yesterday, and if you have not seen that, I recommend taking a look at his slides on how you can basically achieve great performance. As an example, manually specifying an optimum sharding strategy, meaning someone manually going through the possible shardings on a V4 can get you up to 56% MFU on Gemma model, whereas using the automatic policy, you can get up to 54% MFU for that same model. So this significantly reduces the effort that is required to run the distributed workload. Finally, custom kernels are a very important part of the new rapid model design process to achieve high performance. JAX has introduced policy that enables developers to use custom kernels, and PyTorch XLA provides an API to use custom kernels written in policy. Therefore, the same custom kernels that can power your JAX models are available for you to run in PyTorch on cloud TPUs. And PyTorch XLA provides an API to export the model as a saved stable HLO file, which the resulting stable HLO file can then be used for inference either on a device or a server or Android or other environments. So if you are interested, please take a look at PyTorch XLA on GitHub and try cloud TPUs. And I will invite my colleague, Mark Sherwood, to come on the stage and talk about the PyTorch on Edge.
Thank you, Shauheen. All right, so here we are to talk about Google support for PyTorch on the edge. And you might ask yourself, where do you find Google support for PyTorch on the edge? Well, at Google AI Edge. Pretty straightforward. Google AI Edge helps you run AI on mobile, web, and IoT. You'll find all the runtimes, tools, trainings, samples, support, and documentation all in one easy-to-find place. But first, why run AI on the edge? I get that question a lot. You're here to listen to this talk, so hopefully you're already interested, maybe even excited, but let's not get ahead of ourselves. And there's a couple of reasons to run AI on the edge. First is latency. Customers often need apps where low latency is critical. Imagine a real-time video effect, where the ML model is being run on every frame of the video. At 20 or 30 frames per second, you simply don't have time to do a round-trip call to the server. Privacy. Many apps use end-to-end encryption or deal with sensitive data that literally can't leave the device. Therefore, your only option if you want to run ML models on that data is to run it locally. Offline use. For many applications, their AI features need to be available offline. I can't count the number of times that I've been traveling and I pre-download a language on Google Translate, and it gets me out of a lot of binds. I'm really happy in that moment that that ML is running right on my phone. And last, cost. If you have really large applications, oftentimes moving the compute to the local device can save you substantial amounts of money. All right, so let's say you listen to all of that, you say this is great, let's go use Google AI Edge. Well, you wouldn't be alone. Google AI Edge is used by hundreds of thousands of developers just on Android. It's running on 2.7 billion devices, and it's generating trillions of inferences daily. Now, Google AI Edge has lots of functionality, but especially with technical difficulties, we don't have too much time. So let's narrow down on two of them. Specifically, how do you run LLMs on device, and how do you run traditional PyTorch models on device? All right, LLMs. Now, there are many ways to run LLMs on device with different trade-offs, and so Google offers 3 different versions. The first one is Gemini Nano. Gemini Nano is Google's built-in Gen AI on Chrome and Android. I highly recommend you go check that out by looking up Android AI Core or Chrome built-in AI. But there are devices and platforms that don't support Gemini, and sometimes you as a developer want to bring your own language model. And so we're going to talk about 2 ways for you to do that in those situations. The first is MediaPipe LLM Inference API. LLM Inference API is a really easy API to use models that we've pre-optimized that you can just drop right into your application. And then the Google AI Edge Torch Generative API is an API to say, if you want to go to more custom, you want to roll your own LLM, you have your proprietary LLM, or you just enjoy messing around with it, we have a path to bring custom models as well. So here on screen, we have the code that is required to drop LLM Inference API into your application. It's really only a few lines of code. With this, you're able to drop an LLM running fully locally into your Android, iOS, or web application. Here, we see the code for Android, but we have native SDKs for all of our platforms we support. Here we see a demo. This is Gemma 2B running fully locally in browser with a native JavaScript API. It's accelerated on the web GPU through web GPU, and it's pretty fast, enabling you to build very compelling web applications using local LLMs. Here we have Gemma 2B running on Android. Now, all of these demos are recorded on real end devices in real time. We're not speeding this up or altering. As you can see, this is fast enough to be usable in applications and ship really cool features. At the end, we'll have a link to our doc site where we'll have these specific applications and all the code behind them there. So not only do you have the APIs to drop it in, but you have the code examples to go see how we use them. And last but not least, LLM Inference API on iOS. As we say, we support all of the 3 major mobile platforms. And that's really the power of MediaPipe LLM Inference API. You can use the same model, the same weights, and very similar native APIs, and ship across multiple platforms. All right, so LLM Inference API is pretty great. Hopefully I've sold you. You might be wondering, how do I get models for this? Well, we've pre-optimized a set of very popular open source models, such as Gemma 2B. You can visit our doc site and see the full list of open models that we've pre-optimized. But as we said earlier, maybe you want to bring your own version. Maybe there's a model that we don't support that you want to use. Well, that's why we have the generative API. So for the generative API, we provide a really easy way right in PyTorch to reauthor your LLM using our optimized components that transfer very nicely to mobile. And you do all of this natively in your PyTorch environment. And we found that's really important because what that lets you do is use all of the pipelines and the evals that you've already set up in PyTorch with a model that then converts on device. Once you've reauthored the model, you use our Google AI Edge Torch converter. That'll convert it to a light RT model. And then you can use that with the LLM Inference API to build it into your app. let's look at some code. Now, you don't need to read all of this code, although you can later if you want to. The deck is online. But this is what a typical implementation looks like. Note, it's less than 30 lines, and this is reauthoring TinyGemma. At the top, you see we use native PyTorch layers where we're able to. And at the bottom, you use our customized layers to do things that we need to make it run well on mobile. Wonderful. And so, in summary, you can use our pre-optimized models and run them right with LLM Inference API. You can roll your own models fully custom with the Torch Generative API. Once you have that, you have a LightRT model. You can either use our high-level API, rolling that with LLM Inference API, or you can use our lower-level LightRT runtime if you want more flexibility. Today, the Torch Generative API supports CPU acceleration. Expect GPU and NPU acceleration coming very soon. All right, one last summary here for LLMs. So we have Gemini Nano, which is amazing. It's available with limited access on Android and Chrome. We have MediaPipe LLM Inference API that has highly optimized models. And then you can use the Torch Generative API to roll your own fully custom models. Next up, we'll cover how to build great AI-powered apps with traditional ML models from PyTorch. Now, we launched TensorFlow Lite in 2017 with a mission to make it as easy as possible to innovate and bring machine learning models to mobile and edge devices. It's been pretty successful, as we mentioned, with hundreds of thousands of apps using TensorFlow Lite across Android, iOS, and IoT, and our mission hasn't changed. But to stay true to that mission of enabling innovation, we were excited to extend official support for PyTorch earlier this year. We're so committed to this multi-framework mission that we recently rebranded TensorFlow Lite to LightRT. And because LightRT powers ML inference for the entire Google AI Edge stack, that means you have framework optionality through the entire Google AI Edge stack. Find off-the-shelf models or train your own in your framework of choice. Convert your models to a LightRT file in a single step, and then run them with a single runtime bundled in your app across Android, web, and iOS. For anyone here today already using LightRT, formerly known as TensorFlow Lite, or MediaPipe in your apps, you can use new models from PyTorch in your existing packages. Just update to the latest version. You don't need to change any existing models you have in production, and you don't need to build new dependencies. All right, so let's say you want to take a classic PyTorch model and bring it to mobile and convert to LightRT. What does that look like? First, in Python, you import AI Edge Torch. You then initialize your model. You call our converter. You test the output in Python. And then you export to a LightRT model ready to use on device. It really is that easy. PyTorch support for LightRT is available in beta. On GitHub, you can check out the AI Edge Torch or follow live on the link on screen. We've tested AI Edge Torch with over 70 popular PyTorch models and been blown away with both the ease of conversion and the performance that we see. We've built our PyTorch support using as many PyTorch native features as possible. Things like Torch export, PT2E for quantization, and Core A10 for operator expression. If you're running PyTorch models on Android already, either via community-provided conversion to LightRT or via another Edge ML framework, we strongly recommend that you come try this out. We think you'll be really impressed with the performance that you see. We're so grateful that you chose to spend this time with us this afternoon. We hope you have a great afternoon, and thank you.